We have a charged particle moving into the board right now. That's going to be a negatively charged particle moving into the board. We know that it will generate its own magnetic field. The magnetic field that's caused by that moving charged particle will be circular. We can find the direction of that magnetic field by using the wire grasp rule. Thumb in the direction of the negative particle, which is into the page, fingers in the direction of the magnetic field, which end up going counterclockwise. It looks like this. I'm going to call this magnetic field number 1, B1, the magnetic field that's caused by the moving charge. Now I'm going to introduce a couple of magnets. A magnet over here that has a north pole on this end, and a magnet over here that has a south pole on this end. The magnetic field between those two magnets would point this way, from north to south. We're going to call that magnetic field number 2, the external magnetic field. The magnetic field that's there, but not caused by the moving charge. Maybe it's caused by bar magnets, as in this case. Maybe it's caused by the Earth. Maybe it's caused by an MRI machine. Maybe it's caused by some electromagnet. It doesn't matter what it's caused by. It's an external magnetic field, B2, that's there independent of the moving charge. Now, you can imagine if we have a situation like this where the charged particle is moving and it generates this magnetic field, B1, and there's already a magnetic field that it's moving through, then these two magnetic fields just might interact with each other to produce a force. When I have a magnetic field caused by this magnet and caused by this magnet, those two magnetic fields will interact to cause those magnets to attract. So why wouldn't the magnetic field caused by the moving charge interact with the external magnetic field to produce another force? And in fact, if the charged particle is moving perpendicular to the field, that's a big word for the rest of this unit and the next unit as well. We see that word often, perpendicular. If in doubt, guess perpendicular for the rest of the way through this unit. If the charged particle is moving perpendicular to the field, then magnetic field number 1 will interact with magnetic field number 2 to cause a force. But the force is kind of wacky. If we had a charged particle in an electric field, the force is either with the field or against it, right? Remember that? I'm positive the force is with the field if it's an electric field. Negative particle experiences a force opposite to an electric field. With a magnetic field and magnetic force, we have to use another hand rule, a third hand rule, to determine the direction of the force. We call it the hand rule for deflection. And it goes like this. We're going to stick our thumb in the direction of the moving charge, just like we did for the wire grasp rule. Thumb points in the direction of the moving charge. My straight fingers, we're not talking about my curled fingers here. We don't bend them at all. Thumb and fingers are still 90 degrees to each other, but this time they're 90 degrees like this, not 90 degrees like this. Keep them straight. Your straight fingers will point in the direction of the external magnetic field. So in that case, diagram we have here, it would be magnetic field number 2, not in the direction of the green one. Okay, that's a wire grasp rule question, right? If we want to find that circular magnetic field, it's wire grasp rule. If we want to find the force, we're going to use the direction of the external field, B2. So we would say in this case, thumb in the direction of the particle, which is into the page. My fingers, straightened fingers, point in the direction of the field, which is towards the right side of the page. My palm will point in the direction of the magnetic force. Now this is weird. Look at this again. And I'll take it back to that page in a second so you can finish copying that out. But just look at this. Thumb in the direction of the particle, into the page. Fingers this way, perpendicular to that, right? Which way is the force? Direction of my palm, which is toward the top of the page. I got one thing, that's the direction of the particle this way. I got one thing this way, which is the direction of the field. And I got another thing, the direction of the force, this way. All of those things are perpendicular to each other. If the field is perpendicular to the moving charge, the force will be perpendicular to both of those things. Got it? Now, let me let you in on a little secret here. If the charged particle is moving parallel to the field, you can't use that hand rule. But the good news is, if the charged particle is moving parallel to the field like this, or like this, or like this, the force is zero. There is no force. So you don't need to worry about a hand rule when there is no force. If they're perpendicular, use a hand rule. If they're parallel, there is no force. If they're 37 degrees, you can't do that. We don't have to do that in Physics 30. Next year, if you take physics in the university, that's when you'll do it, when you do that question. So there's two questions that you'll see. Charged particles moving perpendicular to the field, use the hand rule. Charged particles moving parallel to the field, force is zero. Here's an example, guys. We're gonna make negative particles green, and we're gonna make positive particles blue here, just so we can keep it straight here. We have a negative particle going which way? Into the page, yes. We have a magnetic field. A magnetic field, by the way, magnetic field will be black. A magnetic field is pointing to the right. Which way is the magnetic force? We're going to say left hand because it's a negative particle, direction of the particle, fingers in direction of the field, which is to the right, palm points which way? Don't say up, say toward the top of the page. Yes, toward the top of the page. Let's do another one. Let's say this time we have a positive particle going towards the right. Positive particle going towards the right. We have a magnetic field that is pointing towards the bottom of the page. Can I use the hand rule for this? Are these perpendicular? Yep. Right hand, thumb in direction of the particle, which is towards the right. Fingers in direction of the field, which is down the page. Palm points which way? Into the page. Palm would point, the magnetic force would be into the page. Let's try another one here. Let's say we have a negatively charged particle again. A negatively charged particle going down the page. We have a magnetic field that is pointing into the page. Can we use the hand rule for this? Are those perpendicular to each other? Yep. So we can use the hand rule. Negative particle going down the page. Fingers, direction of the field, which are going to point into the page. Palm's going to point which way? Towards the left. The magnetic force is towards the left side of the page. One more. Actually, two more. How about this one? You got a positively charged particle going which way? Going out of the page. We have a magnetic force on that particle that is down the page. Which way is the field? We're looking for the field in this one. Right? Not the magnitude of the field, but the direction of the field. How are we going to do that? Well, we use our right hand firstly because it's a positive particle. Thumb in the direction of the particle, which is out of the page. What am I going to do here now? Nope, don't bend anything. This is still a deflection rule. My palm will point down. So instead of being thumb, fingers, which way does my palm point? It's thumb, palm, see which way my fingers point. Thumb out of the page, palm down the page, fingers point to the left. That means the magnetic field is to the left of the page. We're just doing a little algebra, right? On a hand rule. Instead of A, B, solve for C, it's A, C, solve for B. Thumb, fingers, solve for palm. Thumb, palm, solve for fingers. Got it? Last one here. Let's say we've got a charged particle that is a positively charged particle that is going which way? Into the page. We've got a magnetic field which is represented by black here, that is pointing out of the page. What's the direction of the force on this guy? Zero. Good. Can't use the hand rule for this because they're not perpendicular. If they're parallel, it's even easier. Hand rule is not bad, but it's easier if they're parallel to each other because there is no force, and if there is no force, there is no direction. Got a picture of a map up here right now. The only reason I put this up here is to help you see a direction problem that some people sometimes have. Sometimes you get a question with one of these hand rules where it involves north, south, east, west. A question might say, charged particle going to the north, a magnetic field to the west, which way is the force? That's all well and good if we know which way north, south, east, west is, right? But if you happen to be directionally challenged, or if you happen to be in a room where you kind of get turned around and you're not sure which way is north, which way is south, right? We used to write diploma exams in the cafeteria, no windows. People would get turned around all the time and have trouble with which way is north and which way is south. What I want you to do is picture the map of Canada if that happens. Whatever way you're looking is north. Whatever way you're looking is north. We're going to make it up. You guys right now are looking north. Now, not really, right? I say north in quotation marks because really that's what? It's really that's south, right? But when we do these questions, typically when it says north, it means what we think of as north, magnetic south. So that would be north with the way you're looking. This would be south, but behind you would be south. To your right is east, and to your left is west. We know that, right? Because when we picture a map of Canada, eastern Canada, Nova Scotia, New Brunswick, PEI, they're to our right. Western Canada, or British Columbia, is to our left. So if you're in this room and you know that that's north and that's south, that's fine. North, east, south, west. But if you're in another room and you're not sure which way is which, and you're looking this way, make that north. If that's north, then you just have to make sure that that is east. To your right is east. To your left is west. And behind you is south. Does that make sense? Picture the map of Canada to help you visualize that, right? Okay, when we picture that map of Canada, we can see in our minds what's north, south, east, west. So picture that. Doesn't matter which way is really north. As long as you're consistent with your north, south, east, west frame of reference, you're still going to get the question correct. Got it? Okay, that's the only reason that I put that map up. Let's do a quick little thing now for the magnitude of the force, and then we'll do an example question. We know the direction of the force. It's found by the hand rule for deflection. How strong is the force? How big is the force? Here's the equation. F, this of course is the magnetic force in newtons. Notice the absolute value signs. It's the magnitude of the magnetic force. It doesn't give us the direction. There is a direction with the force, but the equation doesn't tell us what it is. That's okay. We have the hand rule to determine what the direction is, right? We don't need the equation to tell us the direction. We need the equation to tell us the magnitude, and it will. What do you think it's dependent upon? What do you think would affect the magnetic force? The bigger this, the stronger the force. The charge, yeah. The charge of the particle. If you have a particle that's twice the charge, then the magnetic force is going to be twice as big. That charge is going to be measured in coulombs. What else? Yep. The distance the magnets are apart? Okay. We'll assume here that we're talking about a uniform magnetic field. And if it's a uniform magnetic field, then that distance would not matter. Okay, if there was a non-uniform field, it would actually, because that would affect what the strength of the field was. Okay, but that takes us to another one actually, the strength of the field. Although we just put the number in for, not the direction, because everything we do here is magnitude only. By the way, the charge, when we sub the charge in there, we're subbing in a positive value for that as well, right? Even if it's an electron. V stands for magnetic field. You guys remember the units for magnetic field? Yeah, it's capital T, Tesla. There's one more thing that we're missing here. You see a space in between Q and B. The faster the particle is moving, the more the force is going to be. Why? Well, because in order to generate a magnetic field, a charged particle has to be moving. The faster it's moving, the stronger the field it generates. The stronger the field it generates, then the stronger the magnetic force. By the way, I should have said, one second here. Let's finish this. The speed of the particle in meters per second. For this one, I should have said not just the magnetic field, but the external magnetic field. Not the strength of the magnetic field generated by the moving charge, but the one that was already there, the external magnetic field. Now, don't write down this next little bit. I'm going to write down something here just to show you something, but you don't need to do anything with this, okay? The equation that you're going to learn next year if you take physics in university is going to look like this. Q times V cross B. Not QVB, not QV times B. QV, actually the absolute value signs disappear then. QV cross B. Well, that turns into, I'm not going to explain why, but it turns into Q times V times B times sine theta. Now, if a charged particle is moving this way and a magnetic field is this way, what's the angle? 90. What's sine 90? Okay, so Q times V times B times 1. The equation becomes QVB, right? What if the charged particle is moving this way and the magnetic field is this way? What's sine 0? What's sine 0? 0. Q times V times B times 0 is 0. There is no magnetic force. What's the angle now? If the charged particle is this way, magnetic field is this way, the angle is 180. What's sine 180? 0. Q times V times B times 0 is 0. There is no magnetic force, right? Make sense? Now, if it's like this, the angle is like 41 degrees. Well, you could actually find the value of that magnetic force using QVB times sine 41 degrees. We just don't have to do that. Now, this equation that we have up here, this highlighted one, or it will be highlighted when my smartboard works, this highlighted one depends upon the charge and the magnetic field being perpendicular to each other. In other words, it's a specialized version of what we see down here. Because of that, we're actually going to stick a little upside down T right there. What do you think that upside down T means? Yeah, it means perpendicular. It means this equation up here is only valid if V and B are perpendicular to each other. Otherwise, you'd have to use QVB sine theta, and that's not one that we have to know. So we're just not going to encounter it this year. Here, let's look at an example, all right? Proton is traveling at this speed into the page through a magnetic field that's directed to the right of the page. So here's my proton moving into the page through the magnetic field that's going to the right of the page. Can I use the hand rule for this? Are these perpendicular? Absolutely. I can use the hand rule for this. I can also use my equation for this because they're perpendicular to each other. Let's find let's find the magnitude of the force first. The magnitude of the force is going to be found by Q times V times B. Q is 1.6 times 10 to the minus 19. V is 5 times 10 to the 5. And the magnetic field strength is 2 times 10 to the negative 2. Remember the magnetic field strength of a bar magnet, typically 10 to the minus 2? It's a reasonable number. I think when you multiply these, we get 1.6 times 10 to the minus 15 newtons. There's the magnitude of the force. Pretty straightforward, right? What about the direction? It's a proton. Right-hand rule. This is not a wire grasp rule. We're not trying to find the field caused by the proton. We're trying to find the force. We're going to say thumb in the direction of the particle into the page. Fingers point to the right. Thumb points which way? Downwards, down toward the bottom of the page. Here's another one that says a 5 times 10 to the negative 25 kilogram particle, charge of 1e. What does that mean, 1e? Elementary charge, yeah. 1 times the elementary charge. Traveling out of the page, magnetic field is pointed to the right. They're perpendicular, so everything we do is valid here. We want to determine the speed that the particle must be traveling near the Earth's surface in order to not be deflected. Wait a sec, not deflected. If it's not deflected up or down, then it must be in a state of equilibrium. That must mean that forces must balance. Okay, two forces balance. What force is balanced here? The magnetic force and what else? Gravity. So we'd say the magnetic force balances the gravitational force. QVB will be equal to m times g. We're just going to rearrange this to solve for v. V is equal to mg over q times b. My mass is 5 times 10 to the negative 25. G is 9.81. Over 1.6 times 10 to the minus 19 times What's B? What was B? Oh, you're not given the field strength. We should have been given the field strength. Let's just say the field strength is 2 times 10 to the negative 2 Tesla. All right, so we multiply 2 times 10 to the negative 2. We calculate that, and we get a number.